Download this code from codegive.com, link in the description below. Gaussian Process Regression Tutorial. Gaussian Process Regression, GPR, is a powerful, non-parametric Bayesian regression technique that is particularly useful for predicting outcomes when the relationship between input and output variables is uncertain. GPR can provide not only predictions but also uncertainty estimates for those predictions. Key concepts. 1. Gaussian process, GP. A GP is a collection of random variables, any finite number of which have a joint Gaussian distribution. It is defined by a mean function and a covariance function, or kernel. 2. Kernel function. The kernel function defines the similarity between points in the input space. Common kernels include the radial basis function, RBF, matérn, and rational quadratic kernels. 3. Hyperparameters, parameters of the kernel function that are optimized during the training process. 4. Prediction, GPR provides a mean prediction and a confidence interval around that prediction based on the learned model and the observed data. Implementation steps. 1. Install required libraries. You will need libraries such as NumPy, Matplotlib, and scikit-learn. If you haven't installed them yet, you can do so via pip. Bash. Pip install NumPy Matplotlib scikit-learn. 2. Import libraries. Import the necessary libraries in your Python script. 3. Generate sample data. Create some synthetic data for regression. 4. Define the kernel. Choose a kernel function for the Gaussian process. 5. Fit the model. Use the training data to fit the GPR model. 6. Make predictions. Use the model to predict on new data points. 7. Visualize results. Plot the predictions along with the confidence intervals. Code example. Here's a complete example of Gaussian process regression using Python. Python. Import NumPy as NP. Import matplotlib.pyplot as plt. From sklearn.gaussian_process import Gaussian process regressor. From sklearn.gaussian_process.kernels import RBF, constant kernel as C. Step 1. Generate sample data. Generate some sample data. np.random.seed, 1. X equals np.sort, np.random.rand, 10, 1, asterisk 10, axis equals 0, 10 points between 0 and 10. Y equals np.sin, x, .ravel, plus np.random.normal, 0, 0.1, x.shape 0, noisy observations. Step 2, define the kernel. Kernel, constant asterisk RBF. Kernel equals C, 1.0, 1 times 10 to the power of negative third, 1 times 10 cubed, asterisk RBF, length underscore scale equals 1.0, length underscore scale underscore bounds equals 1 times 10 to the power of negative second, 1 times 10 squared. Step 3, create and fit the Gaussian process model. GP equals Gaussian process regressor, kernel equals kernel, n underscore restarts underscore optimizer equals 10. GP.fit, x, y. Step 4, make predictions. Generate test data. X underscore test equals np.linspace, 0, 10, 1000, dot reshape, -1, 1. Y underscore pred, sigma equals gp.predict, x underscore test, return underscore std equals true. Step 5, visualize the results. plt.figure, fig size equals 10, 5. plt.plot, x, y, r, marker size equals 10, label equals observations. plt.plot, x underscore test, y underscore pred, b, label equals prediction. plt.fill_between, x_test.ravel. y_pred, 1.96 sigma. y_pred plus 1.96 sigma. Alpha equals 0.2, color equals blue, label equals 95% confidence interval. plt.title, Gaussian process regression. plt.label, input. plt.elabel, output. plt.legend. plt.show. Explanation of the code. 1. Data generation. We create a set of 10 random points and generate some noisy sine wave data. 2. Kernel definition. We use a constant kernel multiplied by an RBF kernel. The length_scale parameter controls the smoothness of the function. 3. Model training. We instantiate the Gaussian process regressor and fit it to our training data. 4. Prediction. We generate a range of test points and use the fitted model to predict their outputs, also obtaining the standard deviation for uncertainty estimation. 5. Visualization. Finally, we plot the observed data, the predicted mean, and the confidence interval around the predictions. Conclusion. Gaussian process regression is a flexible and powerful tool for regression tasks, especially when dealing with small datasets or when uncertainty quantification is important. The ability to incorporate prior knowledge through kernel functions and to provide uncertainty estimates makes it a valuable approach in various applications including machine learning, statistics, and engineering. Feel free to experiment with different kernels and datasets to see how GPR performs in various scenarios.